Hey guys, today we've got this div 3 going on. Let's see. Actually, I have the means to actually hang this up in the background, and I'm gonna do that soon, but I kind of forgot to do that. So yeah, hopefully the scenery should get slightly better. But anyway, we're gonna jump into this. So you have a string S, you have A, B, and C. You can erase A and B or B and C. Erase all letters from the string. So A plus C must equal B. Cool. S. Count. Let's count C minus A. Because every A will remove a B, every B will remove a C, and there's no way you can go otherwise. Right? Like that's gotta be it. Nice. Okay. And okay. Problem B. You get an array. A1, that must be a typo. That type of memory does not support changing the value of an arbitrary element, but you can cyclically shift an array, sort it using no more than n cyclic shifts. Cyclic shift to the left. Oh, by an arbitrary offset. Okay, so you just merge sort it. Or no, not merge sort. Insertion sort. Right? Yeah, okay. So we pick the smallest element, we want to move it to the very beginning. So to do that, we have to cyclically shift it one to the right, but instead we can only do it to the left. So really, what we have to do is just calculate stuff. So for I equals 0, I is let n. Elements distinct? No. Okay, well let's find the smallest element then. Okay. So for that, if AJ is less than MB, MB is equal to AJ, MI is equal to J. If MI is not equal to I, MI. So shift from I to MI, and the distance, the number of shifts will be, what will it be? It'll be the distance between them. So if they're 2 apart, we shift left twice. So it should be MI minus I. And then for Li equals J is equal to I, J is less than MI. No, it should be, we like ripple that element. We shift to the right, yeah. MI minus 1, J is less than or equal to I. Greater than or equal to I, J minus minus. Swap AJ, AJ plus 1. And that will simulate the shift. Now, print the answer. Kind of a tedious problem. Error. Why? sure. Alright, so now this actually did anything, but it doesn't actually print anything because I don't read the array. Cool. Alright, so yeah, this is kind of an annoying problem. So I have to print the operations.size. So yeah, okay. 1, 1, 2, 1. Cool. 2, 1, 2, 3, 1. Yep, move that one there. This one, 2, 1, 3, 2. So we shift left twice, move the 1 over there. Now we get 2, 4. So the 2 is correct. Now we get 3, 4 because we have to swap the 3 and the 4. And then we get 1, 3, 2. So 1, 2, 5. 3, 5, 2. 3, 5, 4. Okay. Now I'll just check the code again. So find the minimum value on the segment I to n-1. AJ is less than MB, breaking ties by taking the smaller index element. Mi is equal to j. Right. If AJ is less than MB, Mi is equal to j. I trust it. Let's go. Okay, ticks. Okay, slow judging. Cool. How many people have solved that? Okay, yeah, kind of annoying. Solves on E1. What are the solves on E1? Permutation P is given. Wait, it's E1, right? Permutation of size n is an array. Wait, this is wait. This is a problem. This is an old problem. Hang on. Wait, what? I don't know if I understand. Add 3 to the end. Oh, it's like, it's the other way around. Okay. So you put the minimum at the beginning? Three, 1, 2. I think that should work. Anything that's not 1, you would not put it. Oh wait, hang on. Okay. Wait. So that is not true. What you will do is you'll pick out the minimum element before 1. Actually, wait, this algorithm is really simple. Should literally just be that. right? Like, you can't do better. You start with that element there. If it's larger, you have to put it in the back, because otherwise it would be worse. And if it's smaller, then you can put it at the beginning. I think it's right. Right? Like, what else would happen? If it's smaller, you put it at the beginning because it's lexicographic. It minimizes the stuff. Yeah, I mean, should be the case. Okay, D is the next one. So many solves on E. Okay, interesting. Let's go for D. Important meeting is to be held. There are exactly M people invited. So the sociability of the ith person is a non-negative integer AI. Maximum number of talks. What? Okay. Why is this a problem? I mean, I'm pretty sure this is just greedy. Yeah, it should just be greedy. Set pair LO. Negative AI I. While st.size, if st.size equal to 1, break. Actually, it should be while this is greater than 1. Wait, this is it, right? Like, yeah. This is well known. It's greedy on the largest ones, always. Do the same thing. Make it Y. Right? No. Oh, wait. If so, let's tee it up again. Take it twice. It should happen because the size is greater than 1. Now push back those two elements, decrement their indices, and continue. Negative so that it takes the largest elements first. 5, 0. Yeah, I mean, there's not much else we can do, right? AI is greater than 0, so we make sure to put that in here. S2 to insert negative AII. Take the smallest ones each time. The largest elements. Yeah, I gotta believe. Nice. Okay, looks like this is the move so far. What else has been solved? So there's solves on C now. Okay, I guess C is the next move. A rectangular piece of paper on a field m by m. Let's denote I vertically, j horizontally. Okay. Ticks. A tick of size d is on the top left diagonally, and d cells on the top right. Okay. Is it asking to check if, what is m? M is up to 19. For every cell, find a tick that could contain it. Okay, sure. Grid. No, okay, so let's see. If I minus d is less than 0, break. Or j minus d is less than 0, or j plus d is greater than or equal to m, break. Alright, so if g of I minus d, j minus d is not equal to star, break. If g I minus d, j plus d is equal to star, is not equal to star, break, plus d. Best I, j is equal to d. Just debug print that. Okay. Now, copy this loop. If gij is equal to star, then so if I plus d is greater than or equal to n, break. If j minus d is greater than or equal to 0, okay, so what we're going to check is first of all, the size should be at least k. D is 2, that means we got here. So this should actually be D minus 1. If, okay, best I plus D, J minus D is greater than or equal to K. And best I plus D, J minus D. It has to be able to reach this. So it should be greater than or equal to D as well, right? So we're 2 above, then it should reach 2 out. Yeah. F is equal 1, break. Do the same thing for J plus D. Should be plus, 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 and plus. Plus plus D. F, pause, and equals F. That one's kind of annoying too, huh? What did I read in? C into N, M, K, right? Yeah. No, yes, yes, yes. No, no, no. Okay. So here, all these are that, all these are that. Here, this is 3, this is 2, so all this is being computed as expected. Here, that's 1, that's 1, that's 1. Perfect. That should be 2, should be 1. That one should just be 1. Yep, and 2. So we're checking for each cell if there is a thing that, if there is a tick that could have created it, basically. Let's check that indexing again, because that's messy. I minus D is greater than 0, and J minus D is less than 0, and J plus D is greater than or equal to M. Break. So G, I minus D, J minus D. Yeah. Yep. This all makes sense. And then the indexing specifically, if we get to 1, 2, and 3, when we get to the third one, and it doesn't work, then we should have stopped at the second, so it's D minus 1, because we get 2 cells up. Now, J minus D, J minus D, J minus D, J minus D, J plus D, J plus D, J plus D, J plus D. So if that is greater than or equal to K, because it must be, and if it's greater than or equal to D, because the difference between them must actually work, then sure. Yeah. Plus plus D, and then seems legit. I just missed that minute, damn it. Okay, so given array, determine whether it will consist of only zeros. Come on. My email's already exposed, it doesn't really matter. Let's just submit this way. Okay, now it works. C. I believe in it. Okay. So cyclic shift of the array by D cells to the right. Awesome. Okay. Alright, what's the problem to go to now? Well, alright, so how do we do this one? Is the algorithm not the same? Oh, minimize the inversions. Okay. Sure. Yeah, that is very different. Okay, E2 is the way to go. So how do we do it? So we do want larger elements at the back generally, but sometimes we can't really do that. So when we choose an element, it will automatically either be at the beginning or at the end. There's not really much we can do about it, right? So like, what do we want to happen? Like no matter what, once we put an element in the deck, the order of the elements within the deck doesn't matter. So really, it's just element by element, which side is better. And the side that is better is, if it goes on the right, it'll make an inversion with everything smaller than it. Okay, that makes sense. So let's create 2 ordered sets. I can't use that. Oh god. Okay. Freaking PBDS. Swear to god. Dude, Facebook Hacker Cup, I got so screwed over by that. Like, I spent 30 minutes trying to import this stupid thing. Well, actually, wait, no, it should work. It should work, right? It should work. I just need to use the right command. If I can find it. That's today. I need specifically this one. Okay, so let's change this. Where are you? Yeah, I'm calling ZHSRC. Okay, so I'm going to do that. Open terminal again. Okay, seems like that works. So now I'm going to find templates. My files are a mess right now. And then ordered set. And I want less equal. Okay, so ordered set. We're using PP for positive and NN for negative. So Cn to X. Ants plus equals min pp dot order of key X. And then the order of key X. This should be negative X. Dot insert X. Two 0 1 0 1 2. Right. Yeah. That should just work. How do I keep missing the minute just by like barely? Swear to God. Yeah. Makes sense. So how does this problem work? Okay, sixth. How does this problem work? You're doing an array of zeros and ones only. Array indices are numbered from 0. Awesome. In one step, the array A is replaced by another array of length n. A new array shifted by d cells to the right. To the right, yes. So if it's that, it's n minus 1. Okay, makes sense. Then, okay. Alright, so let's see. First, we will take the GCD of D and N. And then we will make, because then all these arrays will be separate. All right, now we look for the longest run of ones. If we have even a single 0 within each group, then we will win. But it should be the longest consecutive group of ones that will not die. So that should be fine. Ants is equal to n over d for li equals 0, I is less than g, I plus plus. This should be n over g, my bad. Looking for cyclically the longest group of ones. Yeah, so for I is equal to, now, j is equal to I, j is less than n, j plus equals g, x dot push back ai. I'm gonna do that twice because I want it to be cyclic, then so if y is equal to 1 plus plus cur, else cur is equal to 0. No, wait. It should be the max. So it's greater than or equal to n over g. Okay. Should theoretically be equal to 2 times n over g, but it doesn't really matter. No. Okay. 2, 1. Oh, wait. IT is less than. Okay, yeah, we can go around the array, so that doesn't really make sense. J equals I, IT equals 0. So IT should be less than. So the number of different arrays we have is the GCD. So it should be n over g. Oh, this doesn't even make sense anyway. I wasn't even using j. Okay. J equals I, t equals 0. J is equal to j plus g mod n. Let's try that again. That whole thing was wrong. 1, 1, 2, negative 1, 0. Why? 1, 1, 1, 1, 1, 1. What's happening? I understand that This can go up to 2 times ng, I guess. We can just cycle twice. It shouldn't make a difference though. No. So 1, 0. This is all wrong. What is up with this? What's happening? 0, 1, 2. Oh, wait. No, it should be D, right? Yeah, that's my mistake. It should not be plus G, it should be plus D. Because yeah, that makes sense. There we go. Right. And so the reasoning is, so we take the GCD, that's the number of arrays we'll have. Then for I equals 0, I is less than gi plus plus, start with x. We start at the beginning index, we go around, we jump by d each time, push back to the array. We do it twice around just because we can, so it can be like cyclic kind of. And then for each thing, if y equals 1 plus cur, yeah, so take the longest run of 1s, and then take the worst out of all of those. All right, so if we have all 1s in some array, then we're screwed. Okay, got it. I'm recording, right? Yep, hope so. Okay. Segments. Oh god. Okay. You're given n lengths of segments. The first segment is placed on the axis, so that one of its endpoints lies on the point with coordinate 0. Start of each following segment must coincide with the end of the previous one. That's a lot of tests, huh? When do I get the accepted? So basically, you go to a point, you drive out to some point, then you can drive left or right the next time. Okay. How are we doing now? Alright, so we just got one problem left, huh? Penalty is okay. So we have 10 to the 4th segments. That's something. AI is up to 1,000. So like the current state is like if we were to do some DP, the state would be the position that we're at, or like the length that we currently have and the position that we're at in it. And if we go left to right, it's really easy to make those transitions. But of course, that's too much. So what can we do? And think about the last point where we had an endpoint. So we're interested in DPI is the minimum amount of stuff that could happen, the minimum answer we can get at I, considering the first I minus 1 segments, or considering the first I segments. Answer is dpn. And I guess we can also impose a constraint that we must have had an endpoint here. Like, okay, if we have a bigger answer and we're at the end, it doesn't help to have a bigger answer ever. I'm assuming. Because we're enforcing that we're at the end anyway. And the problem is that well, the worst we could do is 2000 actually, because that's the worst we can do. Because if we have more than 2000, we just go to whichever side is farther away, and we can always survive without creating new stuff. Got it? So once we have that, that will what does that do for us? That should just do it. Okay. So 10,000 and 2,000. All right, so we're gonna have to use ints here. I guess it's supposed to be close. Or I mean, we can. Yeah, I guess we can use the last two rows trick. Sure. DP of 10,000, so 2005, something like that. So we make all of DP a huge number. So let's see, it should be n mod 2 and I. Right, okay, so DP 00, there are no multi-tests, right? There are multi-tests, crap. Okay, they're up to 1,000 tests, so doing memset is actually fine. Cool, because we're gonna have to allocate this much memory anyway, so I guess it's fine. DP of 0 and 0 is equal to 0. Yep. So now for LOJ is equal to 0, J is less than 2002, J plus plus. So first, go left. So NX is equal to DP of I mod 2. So it should be DP of B and what? B and J. So if we go left, then plus min, wait. if we go left, then x minus j is the amount that we go off. For example, if j is 1, x is 3, then we end up going 2 off. And then the new state is, if we go off, then automatically we're done. Otherwise, we move x to the right, or x to the left. Max 0 LO j minus x. Yeah, so dp not b ns is equal to min of that dp not b right. We should set that all to a huge value. dp not b ns and x. Otherwise, we go right. And x is equal to, it's the maximum of that and the new place we're going, which is j plus x. And ns is simply j plus x. If ns is greater than 2001, or nx is greater than 2001, because again, if we're greater than 2000, then there's no point. We're automatically done because we can't really do better. Right? Like 2000 should be an upper bound. So we have like 1500, and then we have 1000. You know what? I'll just say 2500 just to be safe. Or 3000. I don't think it makes a difference. I very much doubt it makes a difference, but it cannot hurt, so I will just do it. So I always bash myself about this stuff. So it does not hurt, but I will do it anyway. dp not b ns is equal to max dp not b ns. I'll do the same thing here. NX. That should be it. That is not it. Okay. Wow. Why though? Oh, min. So that whole transition is in the dirt. Well, I don't understand. That should not change. What? How does that change so much? Oh, I guess because it's actively screwing over some other ones. I guess it would screw over the 0 state. dp1 size of dp, dp0, 0 equals 0. Read into n. Read into x. dp not b. Go left. So dp bj plus max x minus j. Yep. And then j minus x. This one's simpler. It's either we go out or we don't. And the position is simply j plus x. dp of yeah. So everything's min. Okay. And it gets the sample right. That's the most important part. Are we good? I believe in it. We can do it. I believe. There's nothing I can do but watch this. Well, I could try and debug in case there is a bug, but I think watching this is more fun. Why is it running so slowly? All right, that does it. That puts us in 4th, although that will likely not last. So this guy can beat me, this guy can beat me. This guy can beat me. So worst I can do is 7th. But yes, all right, I will take that. That is awesome. Oh wow, he's having trouble, huh? That's not being nice to him. Is he getting jawed? I can see him getting jawed by this stuff. That is something that's happened before, although I won't really load. Yeah, that sounds annoying. Alright, so what's happened within this contest? So, B was a pain. It might have actually been better to go for E1 first, but whatever. But, like, what can you do? There weren't solves on that, I wouldn't have known. So looking at the solve order, so 1 minute, 5 minutes, E1 was a bit faster than B, D was 4 minutes, E2 would have actually been better than C, I think, because that only took 6 minutes. And part of that was just importing the, this, but it's fine. So then C took 10 minutes. So actually, I should have done C after F, optimally. Wow, that is very annoying C, huh? So F took 7 minutes because reasons, and then G took 13 minutes because it took me a bit to see that the coordinates were small. And that's it. That settles it. So let's see how these people do. So when it turns, he has 56 minutes. So when it becomes 01:18 left, then he can no longer beat me. Or they can no longer beat me. But who knows? A lot of people have no penalties too, so that's pretty cool. But yeah, it really just comes down to being faster, I guess. And this is pretty good. Actually, this guy could still win the contest if he got G in time. But it is kind of, I don't know, it's iffy. Implementation is actually not that bad. Okay, so this one was ticks. This one was, oh right, yeah, that one. So that wasn't actually that much. Honestly, these problems were better than I expected. This is comparable quality to a Vovo Div 3, and those are like the vintage ones that a lot of people liked. I think it was pretty good, yeah. Better than some of the other Div 3s we've seen. Okay, so like I was 6 minutes away from the next position. I'm trying to think of how I can win the next one, because winning gives a lot better clickbait than 4th to 7th. I'm here, I'm recording, we're good. Yeah, I don't know. People have 7 problems, they're catching up. Eventually. Cool outcome. Now every time I get a good rank, something happens to it. I get hacked or something like that, and there's just a bunch of pain that happens. So I am not guaranteeing that this position will last, because I'm just cursed with these Div 3s. And it also, the curse always happens when I skip problems. So we'll probably be on E1 or D that I get hacked on. But yeah, who knows? I think that's all we got. So I can do solutions now. That is something I'm capable of doing. Let's get that over with, and then yeah, and then I get back to the grind of school. That was, what was that? That was Bitwise? What did I use otherwise? Anyway, yeah, let me get my tablet hooked up. And then let's do this. And, sorry. I gotta find my pen. I was not prepared for this. I also just realized I forgot to update the sub count, so let's do that quickly. after all the solutions have been submitted, because that's awesome. Yep, okay, back to finding my pen. Ta-da, okay. All right, so here are all the problems. Problem A. So for problem A, you can do you have a string, you can do two things. You can erase any character A from the string, and you also have to erase a B at the same time. Or you can erase any character B, and you also have to erase a character C. You want to make the string empty, you want to see if it's possible. So you want to get rid of everything. So the question is, when is it possible? And the answer is, every time you erase an A, you have to erase a B as well. But this operation is the only way to kill A's. So the number of operations you do is the number of A's that you have. So let's say like Ci is equal to the frequency of I. Then you will do this operation Ca times. Under similar logic, this is the only way to kill C, so you will do this operation Cc times. That is fixed. You cannot do less, because then you will not have any A's, or then you'll have A's still, and you cannot do more because then you'll have too many A's. And the same for C's, right? So if you don't have enough B's to do the operation with A, then you're done. And if you're left with some B's left over, then you're also like, you can't get rid of the B's in any way. So the number of B's you must have is exactly enough to do all the A operations and exactly enough to do all the C operations. So the constraint is that CB must be equal to CA plus CC. And that's it. That turns out to be it. Because then with this constraint, you have enough B's to do all the A operations, and you have enough B's to do all the C operations. So you can get rid of all the A's and all the C's. And then once you do that, you won't have any B's left over because you have exactly enough B's to make that work. So when this is true, you can get rid of everything, and it's the only way you can get rid of everything. So the problem is possible if and only if this condition is true. So the remaining part in code is counting them. You can subtract the character A so that A gets mapped to 0, B gets mapped to 1, and C gets mapped to 2. And then this is just saying if A plus C is equal to B. And this ternary is saying if this is true, do this, otherwise do that. So yeah, that is the condition for this. Problem statement has recently been changed. Oh yeah, okay, they fixed that typo. So, someone make a clarification on that? Did they really not understand the problem, like, as it was? Okay. Whatever. It's probably just in honor of accuracy. How do these people... Still do not have G. Alright, this guy can no longer beat me. Awesome. Because it's been an hour. So now I'm guaranteed at least 6th. Possibly better if this guy and this guy do not win either. Yeah. Okay. Right. So in this one you have an array. You want to sort it. And what you can do is you can pick a subarray and you can cyclically shift it. And what it means to cyclically shift something is, essentially, you can cyclically shift it to the left, which means that this element, every element will move to the left. So this element will move to the left, this element move here, and this element can't move to the left, but it will essentially move around to the end of the array. So this is what happens with a single cyclic shift. Now, you can pick a subarray, and you can do this any amount of times. For example, you can do it k times. So you can do it like, yeah, you can do this shift any amount of times you want in a single operation. So an operation consists of picking a range, doing a cyclic shift with it a certain amount of times, and then that's the operation. So for example, if I have my array be like, so if I have an array of 1, 2, 3, 4, 5, 6, and then I choose to cyclically shift this range twice, then this will be moved. So we'll get this will be the first one because all of these move left. And then this will be the second one, 4, 2, 3. And then this will be the array after the operation. So you want to sort the array. Now recall the sorting algorithms you've learned, because we're going to use one of them. In particular, I believe this is called selection sort, where we actually don't remember the sorting algorithms, but I believe it is called selection sort. So let's do 2, 5, 1, 4, 3. That's a beeping noise. Okay. So selection sort is simple. Pick the minimum, move it to the left. Do that until the array is sorted. So for example here, this will be what happens. We pick 1, we move it to the left so that we get 1, 2, 5, 4, 3. We pick 2, it's already at the left, so perfect. We pick 3, move it to the left, so we get 1, 2, 3, 5, 4. Then we pick 4 and move it to the left, so we get 1, 2, 3, 4, 5. One thing is that the array elements don't have to be different. Be careful with that. But yeah, that's the basic idea. So the question is, how do we do this sort using the operations we have? And well, really, what we can do is we can find the minimum. Then to move it to here, we can say that we're going to cyclically shift 1 to the right, which would mean that this would move here, this would move here, and this would move here. Now the thing is, we can't cyclically shift to the right, but we can do it to the left a bunch of times, and instead we can do it like this. We can just move the 1 2 times over. So if this is L and this is R, then we move the 1 R minus L times over to the left. And then this will change our array. So now we get 1, 2, 5, 4, 3. So then we continue the algorithm, except now we know this element is correct, so we can ignore it. So we continue the algorithm for this part of the array. As an example for the next operation, 2 is here, so we don't do an operation here. 3 is here, so we would move this over. We would cyclically shift this array twice, and then we're left with 5, 4, and we cyclically shift that once. So that's it. The rest is implementation. Finding the minimum is simple. Cyclically shifting it. You have to remember to, it's not just moving the 1 over, it changes the rest of the array too. So you have to simulate that. You have to simulate those changes in the code, so you're not working with the wrong array. And if you have ties, break ties by the smaller, or actually it doesn't matter how you break ties. Yeah, it doesn't matter. Just pick any of the smallest elements and move that to the beginning. It doesn't matter how you break ties. It'll use at most n operations because we're doing like 1 operation per index. So code-wise, read into the array, have a thing of operations. So find the minimum, then do the operation, and then do the operation on the array so that we're working with the right array when we continue. And then print. I'm breaking ties by the smallest index of the minimum. It doesn't really matter then. Yeah, let's move on. This one is a pain, but conceptually it's simple. Implementation-wise, it's actually like not that fun, but conceptually it's not the worst. So we have a grid. On this grid, we can do some operations. In particular, we're going to draw a tick. So a tick, I'll use this V to represent a tick, of size D is saying we pick a position on the array. So say, for example, D equals 2. We pick a position on the array, we color it blue. Or, I guess, like black in the original. It doesn't really matter. Although they color it blue, so I might as well color it blue. We pick an index, we color it blue. Then we also color the D cells in the top left blue. So 2 times we would go up left and paint the cell blue, and for that we would do that as well. So we go like 2 up, or rather D up in the top left. And we do the same thing for the top right. So for example, if D equals 1 here, what we do here is we would only go up once to the top left and top right. Note that we cannot go like off, so this operation would just be invalid. I think. Yeah, because this is not valid. An operation that goes off would be invalid. I think they don't explicitly say that, but it is true. Yeah, because otherwise this one would work. Okay, so an operation cannot go off the grid. So this is not valid even if it does paint these. Actually, maybe they do explicitly say that. Okay, so you want to figure out, you're given the painted grid. You want to figure out if it was painted using only these ticks. So for example, with 5 and 4, you could have something like this. Oh, and if you paint over something, like I do this and then I do this, it'll just be repainted. So it'll stay painted. So for example, this, I could do this with D equals 2. And then I can do this paint with D equals 1. And then everything works out. But there's also another constraint, because if there wasn't a constraint, you could just do this with D equals 0, and then you win every time. So there's also the constraint that every tick must be greater than or equal to K. So the only ticks that are valid are ones with the value of D greater than or equal to K, where K is part of the input. Okay, so finally to the actual problem, because that statement was a bunch. Really all we're asking is, for each cell, is there a tick that could have painted it? And the reason that's fine is because painting a tick doesn't hurt as long as it paints over only the cells that we want to be painted over. So it's fine to paint a tick with the intent of painting only a single cell each time. So basically, like, we're looking at each painted cell. So for example, this cell was painted. We want to find the tick that painted this cell. So in this case, the tick would be here with D equals 2. So where can this tick come from? Well, it can come from any cell in the bottom right or the bottom left. And then when we choose the cell that's going to paint this cell, we need to make sure that it can paint this cell. So it's capable of doing a tick that can reach this, and this tick size must also be greater than or equal to K. So we can check both of these if we pre-compute for every cell the longest tick we can make with it. So we go here, and then we just continue on until we find something in the top left or top right that's either outside of the grid or unpainted. So in this case, the longest tick we can make with this one is 2, because we can go 2 out until we're stopped. The longest tick we can make with this one is 1. The longest tick we can make with this one is 0. This is like -1. We can't even paint it at all. So we compute that for each cell. Then to see if a cell is valid, we're going to look at the bottom left and the bottom right, and we're going to ask what could have painted this cell. If there is a valid way to paint each painted cell, like individually, then the whole thing can be painted. And if some cell could not have been painted at all, then the grid is invalid. Code-wise, this is a mess, but it took me 10 minutes, I think. That was my second worst problem. So we read in the values, read in the grid. I use a string because a string is an array of characters. So then first we compute for each cell, how far can it go? So for each cell, if it goes off the grid, break, or if it's not, like asterisks, if it's not painted, then break. Otherwise, continue. And then, yeah, we're going up left and we're going up right. We're going up left and up right until we reach something that isn't painted, or the end of the grid. In which case, then we're done. It could help to add like a virtual grid where everything outside this grid is unpainted. Like we add another layer outside which says that everything is unpainted. Implementation wise, it might be easier, but it's up to you how you do it. Right, and we continue that on. So now we see for each grid cell, can it have been painted? So if it was painted, we go to the bottom left and bottom right, and we check first if the size of that tick is greater than or equal to k, because it has to be. And in fact, we can start d at k, but it doesn't really matter. Like you can do it however you want. And then the other part is checking if it can reach this cell at all, because if it can't reach, then it's like pointless. What? Yes, if it can reach that cell at all. If so, we found something for this cell, we break, we're good. If we found nothing for this cell, then we're done. So this says if f is false, then pause should also be false. And then print yes or no. Cool, that problem sucked greatly. But yeah, I don't know. I'd say it was the most annoying from the set. I mean, it had merit in that it was like sort of a procedural way of checking if something is valid, which I guess is like, it's an idea, but the implementation was just not worth the idea. So I guess the idea was fine. Conceptually, it was okay to think about, but then it was just painful to implement and make it work. Check the standings once again. I'm in 5th. Okay, so this guy did claim his money, and he got the problem. Other than that, nobody else can beat me. So that's awesome. Yeah, this guy got a couple penalties, but he would have actually... Oh, wait, never mind. No. I'm thinking of someone else. I think this guy, yeah, he would have been above me had he not gotten G so late. There was someone else I was concerned about, too. Maybe they just never got it. Or, no, it was this guy. Alright, he had really good penalty. And this guy would have won the whole contest if he had my G time. That's sad. Okay, so on to D. What was this one? Alright, this one was just standard as hell. Basically, you have an array, like say 1, 2, 3, 4. You can pick 2 indices and subtract 1 from both of them, as long as they're not, as long as they will not become negative. So if I have a 0 here, for example, then I cannot do this because then this will become negative. But this is fine. Making them 0 is fine. They just can't become negative. You want to find out the maximum number of times you can do this. Note that the sum of the values is up to 2e5. So that means that at most 2e5 over 2 operations will be done, which is 1e5, which is fine. So it also asks us to print the operations. So really, this problem is greedy. You pick the 2 largest elements every time. That's it. When you run out of operations, then you can't do any better. Proof is kind of complicated. Let's see. Let me see if is it actually worth it to do the proof? It's kind of just like the desired final state is when you have like all 0s and all 1s. So for example, here you would have like 0, 1, 0, 1, for example. Actually, there are two cases for this problem. One is that the largest element is very big. In particular, this element is greater than the sum of the rest of them. In which case, you would do every operation with this element and you still would have some remaining of this element. And so in that case, it's obvious what the outcome is, that you should do everything with this element and you can't do any better than everything with this element because you'll never run out of this element. So basically you do as many operations as you can with the other ones by doing all of them with this one. So in that case, the strategy works. The other case is that this is small enough the largest element is small enough, and in which case it's kind of more complicated, but the idea is like eventually you end up with a state with only zeros and ones, and that's the optimal state, because then you will guarantee that either the final state is either all zeros and a one, or it's all zeros. And if it's all zeros and a one, then the sum was odd, and that's the best you can do. And otherwise, with all zeros, it's the best you can do. I don't know, it's not really a proof. I don't entirely know how to prove it, but it's just kind of intuitive that that's how it will end up. I don't know. I'm sure this problem has been covered a million times on the internet, so I'll leave it at that. If you do want proof, you can check other places, I guess. I'm not exactly sure how to prove it myself, but it's just kind of intuitive for me. I mean, it should be intuitive in general, but I don't know. Next one. Okay. You have a deck. No, you have a permutation. So for example, 3, 1, 2, 4. And you have a magical list, which is called a deck, or a double-ended queue. And what you're going to do is you're going to look at each element of the permutation, and you can either put it at the front of this list or at the back of this list. So for example, here's something I can do. I could do 3. I can put this at the back, I can put 1 here, I can put 2 at the back, I can put 2 here, I can put this at the front, I will get 4. Yeah. This is actually the worst possible thing you can do for this problem. But what you want to do with this is you're going to get another permutation in this deck eventually. And what you want to do is you want to make this permutation as lexicographically small as possible. And lexicographic, like basically, the first element should be as small as possible, then the second element should be as small as possible, then the third, then the fourth, etc. So basically, you do greedy, you make the first element as small as possible, then second, and so on. So what do we do with these? Let's just go through a bit. So we put 3 at the beginning or the end, it doesn't matter, because there's only one element. What about 1? 1 is smaller than 3, meaning if we put it at the beginning, then it would be lexicographically smaller because the first element would be smaller. So it's good to put 1 at the beginning. What about 2? 2 is larger than 1, so if we put it at the beginning, it would be lexicographically worse. So we put it at the end. About 4 is again larger than 1, so we have to put it at the end. Now we just sort of logicked out each element. And it turns out this is optimal because each decision will if you put a larger element at the beginning, then it will always be lexicographically worse. So really the solution is sort of like greedy-like. We look at each element. If it's larger than the beginning element, then we put it at the end because putting it at the beginning will make the answer worse. And if it's smaller than the beginning, then putting it at the beginning will make the answer better, so we just do that. So here we read in the array. This CV just represents the beginning element, and then if it's smaller than the beginning, then we put it at the beginning, and if it's larger, then we put it at the end. And just because of how lexicographic comparison works, that's just right. Yeah. I'll go over D too. I forgot the code for that. So for D, the code is I'm using a set, and I'm using negatives because the set is sorted, and so I want the largest elements to be at the beginning. So the largest elements will be the smallest if they're negative, so I'm using the negative numbers. Then I take the 2 smallest numbers, well, we have at least 2 non-zero ones, and then add that operation, decrement the frequencies of both of them, and then put the negative versions back in the set. So at every point, we'll just take the 2 smallest elements. Yeah, okay. Problem E2. This is like very different, but the similarity is that there's a deck. Let's do 3, 7, 5, 5. You have a deck, just like you own. What you can do with it is, oh, the operations are exactly the same. You go through each element in order, you put it either at the beginning or the end. What you want to do this time is you want to minimize the number of inversions in the final array. An inversion is a pair of elements where the index is basically a pair of elements that's like unsorted. So basically like this comes before this one, but this is larger than this one. So basically, the index is smaller than the first index is smaller than the second, but the first value is strictly larger than the second. If they're equal, then it's okay. It's not an inversion. So this is not an inversion. But yeah, so how do we? Yeah, what we want to do is we want to put these elements in the deck to minimize the number of inversions. So the key observation here is that when we put an element on, in terms of future elements, it doesn't matter where we put it. So what I mean is like, I'm going to get rid of this bar. So say we have 3. Then when we're putting in 7, regardless of where we put the 7, the 3 is going to be the same no matter what. And in fact, regardless of where we put the 7, the next 5 will be compared to the 7, like, sorry, relative to this 5, both of these arrays are basically the same. If we put the 5 on the end, the 7 will be to the left. If we put the 5 at the beginning, the 7 will be to the right. It doesn't matter where the 7 is relative to the 3. And this continues on. If we put the 5 on either end, it doesn't matter which side we put it on relative to all of the next elements. Because no matter what, for the next element, it'll either be to the left of everything or to the right of everything. Which means when we pick where we put an element, it doesn't affect the future ones. And so the optimal place to put this element is simply the one that generates the least inversions on this turn, because the rest of the turns don't matter. So I'm saying we can greedy this because this turn doesn't affect any future turns. So all we're doing is optimizing each turn independently. So now the question is, where do we put the 5? So the 5 will create an inversion with every element. So say we put the 5 on the left, then the number of inversions created is the number of elements less than 5. And if we put the 5 on the right, then the number of inversions we create are the elements greater than 5. So we want the minimum of these two. So we just need to efficiently find in our deck currently how many elements are less than 5, how many are greater than 5. There's so many ways you can do this. You can, for example, compress coordinates and use a segment tree or Fenwick tree. I use the PBDS set because that makes it super easy. Basically, PBDS is just a set that will also let you count how many elements are less than a specific one. Note less, not less than or equal to. I think. This might actually be bad. I'm pretty sure it's consistent though. I mean, because it passed the tests. And I'm sure the tests had many equal elements, and people have used less equal all the time with this. It's technically undefined behavior, but it's like fine. I mean, I've used it before in a div 3, it was fine. So here, what we do is, the set will count the number of values less than x for some input x. So that will handle the first type. That will handle putting on the left. But we also need to count the number of values greater than x. But this is actually equivalent to counting the number of values that are less than negative x. Because essentially we're just turning the whole number line, like we're flipping it when we're on the negatives. So any value that's greater will be less negatively. Any value that's equal will be equal in negatives. Any value that's smaller will be larger in negatives. So really, we can turn both of these into set operations. One is an array, one is a set with just the positive elements, and the other is a set where we take the negative version of each element. Since again, it sort of just flips the whole number line around. And even if these elements can be negative, it doesn't matter. Because again, we just want to flip the number line around. So here, I create a set for positive elements and negative elements, and then we take the minimum of the positive and negative, and then we insert into both of them. Be sure to insert the negative element in that. Order of key does exactly what I'm talking about. It will count the values. PBDS, there's a blog on it. Basically, you put these lines in. Less equal will make it so you cannot... let's see. Less equal will make it so it'll handle equal elements. It'll consider them differently. With less, it will act like a normal set, and equal elements will be just considered as a single element. So if you insert two 2s, you'll only have one 2 in the set. You can also make a multi-set. It's kind of a pain. I think this is technically undefined behavior, but it has not failed me yet, so I don't know. I'm sort of going against my own mantra here, but it's fine. Yeah, so that's what we're doing. Each element is optimized individually. Problem F. You have an array of zeros and ones. It is zero indexed for whatever reason. I don't know why they do that, but yeah. Okay. Oh, God. Oh, this freaking heat. Jesus Christ. Oh. Ow. Oh. God, I hate this heat. Can't wait for it to be winter. All right, so the way this works is we have an array of zeros and ones. A single operation will be to it'll be to cyclically shift the array to the right by some value d. And cyclically shift is the same as it was in B. Essentially, to the right, we move each element d across. So if d equals 1, we would move each element 1 across. If d equals 3, we would move each element 3 across. So this would move 3 across here. This would move like 3 across, but it would be like, it's sort of like circularly. So this would go here. This is 1, then this would be 2, then this would be 3 across. So really this one, so really every other element would end up moving 1 backwards. Because this would go here as 1, this would go here as 2, and then this would go here as its third move. In other words, we're cyclically shifting the array 3 times. So this is one cyclic shift. And like that. In other words, we're setting every index I will move to I plus D mod n. Because when we go around, we're basically going from n to 0, and that's the equivalent of mod n. So cyclic shifts are really just like mod n. So that's kind of cool. Yeah, so anyway, that's what a cyclic shift is. So what we're going to do is, I'm going to leave that up. I I told it to text mode. I don't understand why it's not text mode. So for example, say d equals 1. Then the new array would be 1, 0, 0, 1. Then what we do is we're going to bitwise AND these two arrays together like element-wise. So this will become 0 and 1, which is 0, this is 0, this is 0, this is 1. Bitwise AND is true. It's 1 only if both of its arguments are 1, otherwise it'll become a 0. So really these are all the possible arguments for bitwise AND, and this shows the outcomes for all of them. So what happens? What are we doing? Oh, I'm having my jaw hurt because of this heat, apparently. That's awesome. So ultimately, we want this. So we're going to do this operation a bunch of times. Ultimately, we want the array to be completely filled with zeros. So in this case, say we do this operation again. The shifted array will be 1, 0, 0, 0. And so the final outcome will be 0, 0, 0, 0. And we're done. The array is full of zeros. So we're asking, after how many operations will it take? How many operations will it take for the whole array to be 0? Or sometimes it's not possible. For example, if the whole array is 1, then everything will be 1 forever. So this sort of has to do with number theory a bit, which I'm actually doing a stream on pretty soon, I think. I hope. So we have this array. Let's consider a case like this. And let's say d equals 2. Also, d is fixed. We don't choose the d for the operation. We will always cyclic shift a certain amount of times. So in this case, if d equals 2, when we cyclically shift, this will move here, this will move here, this will move here, this will move here. We get the same array. We always get 1s. Even though we have even though we have zeros in the array, we will still always infinitely get 1s. And the reasoning is that sometimes you end up with like two separate parts or multiple separate parts. Because here, if d equals 2, these parts are completely independent from each other. The first and the third element is independent. Should not have used. The elements 0 and 2 are independent from elements 1 and 3. Right, so, yeah. So how do we know what's independent and what isn't? Basically what we can do is we can walk along the array and we can count the number of steps it takes for us to get back to our original index. And let's take, for example, 6. So like 1, 0, 1, 0, 1, 0. And then let's have d equals 4. So we go up 4 here, then this will take us back here, and then this will take us back here. I don't know how to lead into this, but it turns out the number of groups we have is the GCD of n and d. That is the number of separate groups we have. And the reason is that every time we advance by d, let's let g equals that. Every time we advance by d, our value mod g doesn't change, because d mod g is equal to 0 by definition, and n mod g is equal to 0. So when we mod n, which is really subtracting n maybe multiple times, our value mod g will not change. And when we add d, our value mod g will also not change. So each independent value of like having like I mod g is equal to x, each group of like residues modulo g, or the remainders, form their own group. because you cannot go from one remainder to another remainder. And as it turns out, by some number theory like theorems and stuff like that, if two things have the same remainder, they can always get to each other eventually. Yeah, there's some more number theory stuff behind that. But yeah, so basically the things get grouped up based on their value mod g. So we take the GCD of n and d, and essentially now what we need to do is we need to collect the arrays in that order. So for example here, we basically have two independent arrays. We have 1, 1, 1 and 0, 0, 0. And now we're going to solve these arrays independently. This will take 0 moves to work. This will take infinite. So the answer is infinite because we can't mess with this one. Let's say we had a different array and d is still 4. So for example, 1, 0, 1, 0, 0, 1, 1, 1. So in this case, we create the arrays as follows. We jump by d until we get back to the original index. So for example, for this one, we get 1, 1, 0, because we start here, we go here, and we go here. For this one, we get 0, 1, 1. Now, the answer for an individual array turns out to be the longest group of ones that we have. Because every time we do a cyclic shift, since we're basically shifting to the left once, when we jump by d, this basically gives us the elements in the order that like the cyclic shift will visit them. So like this element will be ANDed with this one because they're 4 apart. And this element will be ANDed with this one because they're 4 apart. And this element with this one because they're 4 apart. So basically now we can treat it like we're cyclically shifting by 1 because we're saying that this is like the order of the cyclic shift. So now when we do an operation, this 0 will take out exactly one of the elements in this group of ones. And this element will survive because it has a 1 to the left of it. So this will die, but this will survive. And so say we have like 5 ones, then it will take 5 operations to get rid of all of these. These 4 will remain alive for the time being. This will be 0. Then we kill it with this one. And it takes 5 operations because we have 5 ones that are consecutive. So the answer is the longest group of ones within this independent array. And if everything is 1, then automatically we're done. It's infinite. We can't do anything about it. Now, be careful because we have to consider the longest group of ones like circularly. So for example, here, this is 2 because this is a group of ones. So the way I usually handle this is I just append another copy of itself. So you set A equal to A plus A. So in this case, I would do 1, 0, 1, 1, 0, 1. And that way, now, anything that wraps around will now be like adjacent to the second array because that's the beginning. Like you put the beginning next to the end. And if it has all 1s, it will still have all 1s, and otherwise it'll do what you need. So you just duplicate the array each time. Find the longest run of 1s, and then take the worst one out of each independent problem based on like remainder mod g. And then print infinity, or the longest group of 1s corresponding to what you find. Of course, if everything's 0, then you have no 1, so the answer should be 0. So here, we have values, read into the array, do GCD. Then the number of elements in each group will be n over this g, because we have g groups. It turns out all of them are equivalent. Because like this is basically this group, but you move everything 1 over. And so if you have g groups, you just move everything 1 over that many times. And so they're equivalent in that sense. So because each group has the same number of elements, the number of elements in each one must be n over g. So here, this is basically the main loop. I'm starting, you fix like the starting position For example, you can start at 0 for the first group, you can start at 1 for the second group, etc. Then you jump by d each time up until you get n over g elements. In this case, I'm going up to 2 because, again, I'm duplicating the array, so I'm having 2 of each element included. And to jump, you move up by d, and then you mod it by n because you're going around in a circle. So then this is our array. We count the longest group of 1s, take the best of them, and then print the answer. If we have at least ng 1s, or the longest group of 1s is at least ng, then it means that we have all 1s in some part of it. So that's the worst we can do. All right, last problem. Then I can get out of this heat. For Christ's sake. I hate my door. I would not recommend this place. If I get popular enough, I'm gonna slander the hell out of this university. Okay, so last thing. I'm gonna think of it like this. You have a car. And then you can go and then you have a car and you have an array for, like, for example, like 6, 2, 3, 9. At each point, you can either move, for each AI, you can either move left that amount or right that amount. So for example, say I move right by 6. Then I can move left or right 2. Let's say we move left. I can move left or right 3. Let's say we move right, or left. And I can move left or right 9. Let's say we move left. So now the coordinates I visited in order are 0, 6, 4, 1, -8. And basically, what we're trying to do is we're trying to minimize the absolute difference. No, well, yes. We're trying to minimize the difference between the rightmost coordinate and the leftmost coordinate. So in this case, the difference would be 6 minus -8, which is 14. So in total, we sort of traveled a distance of 14, which is, we can do better than that. Somehow. How do we do better than that? Right, okay, yeah. So the best we can do, no, sorry. So in this case, the total, like, the span of the distance we traveled is 14. So a better way to handle this case would be this. We start here, we move over 6, then we move over 2, then we move over 3, and then we move over 9. And that way, in order, we visit 0, 6, 4, 7, -2, and the total distance is 7 minus -2, which is 9, or the total span is 9. So that's the best we can do. Now, the first thing is, n is up to 10 to the 4th. The second thing is, the value is up to 1,000. And the reason that's important is because consider what happens when we have a long enough segment. For example, say the current span we have is already 2,000. Then no matter where we are, we can move in the direction that's farther away. So for example, say we have a strip of length 1,000, which is the longest we can get. We can move in the direction that's farther away. And because this is 0 and this is 2,000, say we're at x, then the maximum of the two distances we can travel, which is either x to the left. Okay, that wasn't a text. Which is either x to the left or 2,000 minus x to the right, has to be greater than or equal to 1,000. Because if one of them is smaller, then the other one is 2,000 minus that, and therefore it's larger than that. Or it's greater than or equal to 1,000. So once we have a span of size 2,000, we cannot do worse than that. So really, what we can do is we can define a DP array. So DP of I, which is I movements or segments or like trips that we've done. And we're at position X relative to our current span. So for example here, like the coordinates we could have are between 0 and 2000, inclusive of both, and we're at X within this span that we're at. It doesn't matter where the span is in the number line. It could be like super far to the left or super far to the right, or either. It doesn't matter. Because all that matters is if we expand the span to the left or to the right. So the only position that matters is our position relative to the beginning of the span. So in this case, that signifies that this distance is X. Transitions are fairly simple. If we move left, our position will change, and it will change to the maximum of 0, and say we're currently at X, and then we move Y. So for example, say our next move will be like Y. So it's the maximum of 0 and X minus Y. Because we're at X, we move Y left. How much does the span increase? Well, this would be Y minus X, because that's the final coordinate we end up at. In particular, it's 0 minus X minus Y, because that's the coordinate we're at. So the amount we increase the span by is the maximum of 0 and Y minus X, because that's how far we can end up to the left of our starting position. If we move right, it's even simpler. The position is just X plus Y, and the span is whichever is larger, the current span or the amount we move by. So the span is like the maximum dp of I and X, or X plus Y. I think it makes more sense if you see it in code. In terms of memory, it's kind of a pain. So what I'm doing is I'm doing a trick where in this DP, you only care about the like DP of I and something will only rely on DP of I minus 1 and something. So I minus 2 to 0 is irrelevant. We can get rid of it. We don't really care about it. So all we really care about is the previous row of DP states. And that's what I'm doing here. I'm only storing in this code the previous row. And then we overwrite like the next row. So one way to do that is using mod 2. You can also use like vectors or something to represent the rows. It doesn't really matter. The point is you only store the last 2 rows of the DP. And that makes the memory like almost nothing, because now it's just 2 times 3000. So this memset will not TLE, even though you have to be careful normally. Sometimes memset will TLE if you're not careful. You can also make the memory work using integers. Like you just use ints and it'll fit, but whatever. So yeah. So if we go left, I've made my code like pretty clear, I hope. So then the new size we could have, the new position, no, this is the new size. I sort of mixed these up actually. This is the new state, this is the new size. So the new size we could have is the formula that I said. It's the old size plus however much we end up going to the left. And the new state is just the new position, like wherever we end up. Either it's 0, or if we don't fully extend, then it's just the old position but minus X. think that made sense. Yeah, and then this is going right. This is even simpler. It's just the maximum of the old length and the new length. And the new state is just we go right to the x. And we also make sure that if we do end up going larger than 2000, then we ignore that state because we can always do better. I made it 3000 just to be safe, but I'm pretty sure if you made these numbers 2000, it would still pass, I think. But again, I just wanted to be safe for myself. And then we're considering like, we push these out to the next row dp. Then we take the minimum over all possible ending positions because it doesn't matter where we are. The only thing that matters is how long our span is, like the largest coordinate minus the smallest coordinate of our whole journey. And then yeah, that's it. Hopefully that made sense. I will timestamp this stuff as usual. And yeah, 5th. Not bad. Not bad at all. I would consider it good. Oh my god, that is not a good outcome of that. Jeez. Alright, how much would it have been without that? So 6 plus 30, so 90 penalty, so 251. How good would that be? That'd be pretty good. Yeah, like top 40. Wait, what? Oh wow, that's like a really sharp drop. We started late, of course. Of course. Kind of interested in that actually. So say we subtract out 8. Huh. That'd be very, very close to mine. Okay, sure. That'd be funny. Alright. Yep, I will leave it here. I hope you enjoyed. Goodbye.